Okay, so we are working through lecture set 4 right now, which is devoted to the one-way ANOVA procedure. So as a reminder, the one-way ANOVA procedure is a procedure that we are learning how to use when we want to determine if there's evidence of a difference among 3 or more population means. We call it a one-way ANOVA because we have one response variable of interest and we call it a one-way ANOVA because the response variable of interest to us is essentially split into groups based off of one factor variable or one quantitative variable. So the one way in one-way ANOVA refers to the fact that there is only one factor that's splitting our response variable into 3 or more groups, which are sometimes called treatments. We'll sometimes just refer to them as separate populations, but this is the idea. All right, last class we left off kind of looking at just like a general idea of what ANOVA data could look like. I mean, this is subject to change depending on the experiment, but effectively what you can expect to see are 3 or more samples of data that could be arranged in rows, they could be arranged in columns. If they could be one column of data with indicators for the group beside them in the second column. So there are actually many different ways that we could observe data that should be submitted to an ANOVA. But the big thing to look out for is that you have 3 or more different samples of information representing 3 or more different populations, and you want to compare the means of those populations. Because we have multiple populations, we would therefore extend all of our previous symbols to these different, to this situation. So what I mean is when we think about the 2 sample t-tests, we had N1, N2, X bar 1, X bar 2, little s1, little s2. Now, in the general case where we have K populations, we're going to have N1, N2 to NK, X bar 1, X bar 2 to X bar K, S1, S2 to SK. So little k is just a letter that we use to represent a count of all the populations that we're working with. So k can be 3, 4, 5, 6, 7, etc. Okay, now we can also introduce the symbol, the letter J. Though, to be completely honest with you, like these symbols and whatnot, we don't need to worry about them too much, but they do appear in some of the formula. So we can set them up right now, but you can kind of get away with not fully utilizing them once you start working through the experiments. But just for completion's sake, so little k counts the number of populations that we have in the system that we are interested in. Little j is an index that tells us which population we are working with. So when j is equal to 3, that means that you're working with population 3. When j is equal to 10, that means you're working with population 10. When j is equal to k, that means you're working with population k. So we can say that we have a sample size, a sample mean, and a sample standard deviation for each of the k populations. So n subscript j, x bar subscript j, and s subscript j. We also introduced the symbol capital T to represent the total value for the sample we are working with. And the total value is simply the sum of all numbers in the sample. So it would be the sample size multiplied by the sample average. So we could say here, for example, Tj is equal to little nj times x bar j. So x bar j is equal to Tj over nj. So the Tj is actually just the sum from I equals 1 to nj of each yi in j over nj. Okay. Or I guess I should say x because I was using x before. And then finally, we have what we call the grand mean. So we're going to differentiate between different means based off of our explanation of within and between variance that we talked about last class. So the grand mean is the average of every observation in the sample. So that is actually just the generic formula for the sample mean. So it's the sum of all values that we observed across every single sample divided by total sample size. So we would have a mean for each of the samples, and we would have an overall mean, which is the average across all samples. And it's actually also the average of the sample means. Okay, when we are working with an ANOVA model, we express when we are working with the one-way ANOVA, we can express our assumptions about the data through the following formula, which is given in equation 1. So equation 1 is telling us that the data, which is xij here, so this part is the data, so just the values that we are working with, is equal to a mean plus a normal random variable. Okay, so in the context of the distributional symbols that we've introduced in lecture set 1, what we are actually saying here is that the data is normally distributed with its own mean and a constant variance. So basically what we're saying here is each observation belongs to a normal distribution with mean mu j and variance sigma squared. So in a practical interpretation, what this is telling us is that we believe the data are all normal. So we assume normality across every observation. We believe that the data all come from normal distributions that have the exact same variance. So there's an assumption of constant variance across all of the populations. But each observation can belong to a normal distribution that has its own mean. Okay, so the ANOVA assumption is essentially saying all of the data are normal, all of the data have the same variance, but the means can be different for each group. Okay, so we're focused on that idea of separating between means, but we assume that the variance is constant across all of the groups. Okay, so the overall set of assumptions for an ANOVA experiment are summarized on slide 17. So they're very similar to what we had in the case of the two-sample t-test. The only different, or the biggest difference, is that with the ANOVA, we assume the variance is constant across all of the different populations that we are studying. The two-sample t-test that we looked at before allowed for us to parameterize, or allowed us to account for different variances. So the two-sample t-test we studied in lecture set 3, well, the independent two-sample t-test that we studied in lecture set 3, that test statistic had a denominator of square root s1 squared over n1 plus s2 squared over n2. So effectively, it assumed the variances were different, but even if they were very similar, you could plug each of them in separately. With the ANOVA, we remove the assumption, or depending on how you look at it, we have an additional assumption that the variance across every single population in the study is exactly the same. Okay. So from a visual standpoint, right, you can think of an ANOVA problem. So if you imagined a grid or a like a plane like this, So here's, well, we'll just put 0 here for argument's sake. So this might be mu1, this might be mu2, and this might be mu3, right? So each of these represent their own normal population. So we would be taking this normal curve, okay, and we would just be centering each of them. Whoa, sorry. At their own mean, like this. Okay. So the idea here is constant variance, all normal differing means. And in this particular situation, you can see that the illustration that I have sketched here represents where we would have different means. But in a problem, what we wouldn't know is if these distributions are separate or if they would be overlapping with each other. So you could have two bell curves that are almost sitting on top of each other, and then we might not be able to distinguish between those. So the general ANOVA problem says assume all of the populations are normal. They all have the same variance, which means that you're placing the same bell curve on top of each population, but you're centering them at a different point. And then the question really is, if we compare the variances, is there evidence that the center of these normals are far enough apart to say that they're different from each other? Okay. Does anyone have any questions? Ugh, it's not very good. Okay, so verification of the assumptions for the ANOVA are going to work very similar or almost analogously. When we want to verify the assumptions of an ANOVA, we're going to follow processes that we already had talked about for the 1 and 2 sample t-tests. Okay, so for example, the first two assumptions, the SRS assumption and independence between the samples, we have to have some idea of where the data came from. Okay, so that's kind of the standard explanation for verifying those. Normality assumption, we can still use a QQ plot. We're going to show that when we actually check the assumption, we can use a QQ plot for all of the data at the same time. And we're going to talk about this at the end of the next lecture set, when we'll discuss residual analysis for verifying normality assumptions. We're also going to look at this in detail in lab. So you'll see illustrations of how to verify these assumptions in lab. But in general, it's the same strategy as before. You're just building a QQ plot of the data to see if it looks normal. And if you use, since all of the values are normal, you can consider them all at the same time because their cumulative distribution should also be normal. The constant variance assumption can be tested in a lot of ways. So subjective approaches to testing constant variance would be through using box plots. So we can construct a box plot for each of the different samples that we have, and then we can compare the spread of those box plots. So if we were to do that, you would probably expect to see something that looks like this. So if we have our axis here, so we'll call this X. If you built a box plot for each population, you would expect to see symmetry because of the normality assumption. And then you would expect to see that all of the box plots have the same range. So if the means are different, they're not going to be lined up exactly. But when you look at the spread of the plot, this would indicate equal variance. Okay, and this would be mu1, mu2, mu3, just for lack, like population 1, population 2, population 3. Okay, if you wanted to violate this, so let's say that we added in a fourth group, but its box plot looked like this. Okay. Does that look different enough? No, let's make it a little more extreme just to get at the point. Something like that. Okay, so this would be a violation of that assumption. So now you have a box plot that's clearly doesn't really look symmetric, but also doesn't have the same range as the other plots. Sorry, I just want to get it like perfect. We'll just do it like this. Okay, so you can see that the spread of this box plot is much smaller than the spread of the other three. So that would indicate the variance is different in that group. So that's one way we can go about it. We can also use what's called the rule of two. So the rule of two says if 0.5 is less than or equal to max Sj divided by the minimum Sj is less than or equal to 2, then variances are equal. Okay, sorry, I'll just clean this up a bit. So the rule of two basically says take your largest standard deviation, take your smallest standard deviation, divide them by each other. So you can do max over min or you can do min over max. It doesn't actually matter which way you do the ratio. If they're within a factor of 2, which just means if they're between 0.5 and 2, you can assume the variances are equal. Okay. This is a very crude test of equality. I mean, certainly there are better ways of going about it, but this is something else that we can use. We can also use what's called Levene's test. And I'm going to talk a little bit more about this momentarily. Levene's test is actually a formal test of variance equality that gives you a p-value in the end. Okay, so this would be kind of like a Shapiro-Wilks test for normality. And SPSS will give you the result from Levene's test automatically when you do the ANOVA. So you can use this to check the assumption automatically in that way. Okay, sorry, Jen, for the box, the whiskers, or both? The whiskers. You want total range of the whole data set. So you would go whisker to whisker. So these are just some ideas, like different approaches that have been, that are commonly used to check for equal variance. I mean, obviously you run into subjectivity issues with these kind of things, and depending on how strict you are, you might go one way or another. I think the nice thing about the rule of two and Levene's test is it gives you an exact criteria that you have to adhere to. So if you're not within the factor of 2, it's like, okay, I'm not within, I can't assume it. And Levene's test gives you a p-value in the end, so you can reject equality that way. So these are typically a little more satisfying, but the box plot approach is also used quite often. And if the ranges of the box plots are the same, you will expect the variances to be the same as well, especially in the case of symmetry. But if you start to add skewness in and those kind of departures, you have a whole other kind of issue to deal with anyways. All right, so what is Levene's test? So Levene's test is a formal hypothesis test about variance equality. So the null hypothesis is that all variances are equal against the alternative that not all variances are equal. So Levene's test is essentially the one-way ANOVA for variances. So this test is very useful for checking the constant variance assumption of a one-way ANOVA. We're not going to go into the detail about how to conduct the test in this class, but again, SPSS will spit out output for Levene test. So you can basically say, given a significance level of 0.05, I have evidence to reject the null, or I do not have evidence to reject the null based off of the p-value of the Levene test. And this would be done in the usual way that we make conclusions about null hypotheses. The only difference here is that we're probably, I mean, not to imply that we root for a result either way, but you would be looking to not reject in this case if you want to use the ANOVA. Okay, so the ANOVA procedure is based off of the idea that we can compare variation to make a decision about whether or not means are different. The two kinds of variation that we will compare are called the between treatment variance and the within treatment variance. In the context of the ANOVA hypothesis test, these will appear as what are called mean squared treatment and sum of squared treatment. To see the derivation of how we get to these variances, we start by writing out what are called the sum of squares. So from any ANOVA experiment, we can always compute SST, which is SS total. Okay, so this is for any, not just ANOVA, but we'll just write for now for any ANOVA. So the SST is simply the difference between each observation in the data set and the overall mean squared added together. SSTR is our representation of the between treatment effect. So you can see that the SSTR is squared difference around grand mean of each group mean. Okay. The SSE is the within group representation of the sum of squared difference. And if you look closely at this, you can see that what the SSE actually is simply the standard deviation of the group multiplied by the sample size minus 1. Okay, so if you think about the form of the standard deviation, or sorry, this would be SJ squared. So if you think about the form of the variance estimator or the sample variance estimator, the sample variance estimator is S squared is equal to the sum from I equals 1 to n of xi minus x bar squared over n minus 1. This SSE here is the sum of each observation within its group minus its corresponding sample mean squared. So this is the numerator of the variance expression for that group of interest. Right? So the formula in equation 2 is called the one-way ANOVA identity, or more common, or is called the one-way ANOVA identity, and it's also referred to as a decomposition of the sum of squares. So it's basically saying we have a total sum of square and we can break it into different components. And this is the crux of where the ANOVA F test comes from. And what we will see in the coming weeks is that we can take a total sum of square and decompose it into different parts and use those parts to make hypothesis tests about different means. And that's kind of how all ANOVAs work across the system of popular ANOVAs. All right, if we need to, in a practical setting, the sums of squares can be computed using either defining formulas or computing formulas. Typically, the way that we would approach this, we would find SST and we would find SSTR. Those are usually the easiest sum of squares to compute by hand, whereas SSE is a bit more cumbersome. So we leave that for last, and then we just exploit the decomposition of the total sum of squares to find SSE. Just trying to think if there's a situation where you're going to be forced to go through the ringer with this. I think there might be for a randomized block design, but the point is that if we have to do it by hand, this is how we would go about doing it. And for the SST is just find the mean of everything in the data set, and then take each observation, subtract that mean, square it, add all of those together. So that one is pretty straightforward. The SSTR is also pretty straightforward. You find the mean of each group, you find the overall mean, you do the difference of each group mean minus the overall mean squared, multiplied by the group sample size, add those together. Once you have those two, it's easy to get SSE. So that's the path that I would recommend if you have to do it by hand. Okay, so the actual ANOVA F-test is a test of mean equality against the alternative that a difference exists somewhere in the system. So it's important to note that when you are running a one-way ANOVA, your null hypothesis will say all the means are equal. The alternative does not say all means are different. All means being different is a possible outcome of the alternative hypothesis, but we do not state that as the formal alternative. Our alternative is simply that a difference between two means exists somewhere in the system of means. So theoretically, if you have a system that has 4 means in it, so mean 1, 2, 3, 4, if you run an ANOVA on this system and all the assumptions are in check, if the null hypothesis is rejected, it could be only because mean 1 and mean 2 are different, but all other means are equivalent to each other. So you only have to detect one difference among any set of means, any pair of means, I should say, in order for rejection of the null to occur. Now, with that being said, one of the questions that's going to come up is, okay, I rejected the alternative, but how do I know where the difference is? We're going to talk about that in the next lecture set. We do that through what is called multiple comparison, which is basically just an ambush of t-tests and intervals across the whole system. Okay, so formally, to compare the variation in between the samples of interest to us to within the samples that are of interest to us, we take our sum of square values, so SSTR and SSE, and we divide by their corresponding degrees of freedom, which are given here and here. So this is DF, TR, and this is DFE. Now, once you do this, effectively what you are doing here is you are just constructing your estimates of the variance between the sample means and your estimate of your total estimate of variance within each of the samples. Then you take MSTR and divide by MSE, and you have a test statistic, which is an F value. And the reason it is an F value is for the reasons that we stated at the start of the lecture set. So if you assume all the data is normal, and then you compute variances, you have a chi-square. And then if you take the ratio of these two chi-squares, you end up with an F. Okay, so all this being an F value follows theoretically from the fact that we start from normality. The degrees of freedom for the F statistic are the same as the degrees of freedom numerators for the MSTR and MSE. Okay, so we're just using our F table on the first and second DF to either find a critical value or a P value. All right. So the F test itself, now we talked about this at the start of last class, but the F test is like a one-sided test, okay? It's one-sided in the sense that we only ever reject in that upper tail or in the skewed tail of the F curve. So if you recall, the F curve is a strictly positive curve that starts at 0 and then skews to positive infinity. So when it skews to positive, in the tail that's skewing, that's where we perform our test. Okay, so the F value itself is a ratio of these two variances. So we are going to observe a large F value when the between mean variance is much larger than the within group variance. So when MSTR is much bigger than MSE, right? So if we observe a very large F value, this is going to give us evidence of a difference between means. And if we observe a very small f value, this is going to give us no evidence of a difference between means. Okay. Now the point of this slide is to emphasize that this idea of being one-sided or two-sided, while you can see this visually when you look at the structure of the F curve, the real reason we would consider this a one-sided test is because all of the F values are going to be positive numbers, and you're always going to be, in that sense, rejecting on the positive side of the curve. So, sorry, let me put that differently. All of the F values are going to be positive numbers. So it's the magnitude of the F value that determines whether or not you are going to be rejecting or not rejecting the null. If we think back to the way that our t-test worked, it was still magnitude of the test statistic that determined whether or not we would reject or not reject the null. However, the big difference there was you could reject for very large positive values, or you could reject for very large negative values or very small negative values, depending on how you want to look at that or think about that. But here we're always strictly working on we're always strictly working in the positive domain, and it's purely the magnitude of the value that determines if we're going to reject or not reject. Okay, when we work through the steps of the ANOVA F-test, our third step of the process typically involves the construction of what is called an ANOVA table. And the ANOVA table is shown on slide 24. Now, the idea here is on step 3, when you compute the F value, you can summarize all of the information that you need for the F value inside this table. You don't have to use the table. Like, if you don't want to, if you just want to write the numbers out, you can. But the thing that's nice about the ANOVA table is that it highlights the relationships between the degrees of freedom and the decomposition. And it just orders the information in a fashion that's fairly easy to digest and work with. So for example, you can see that the first two columns here, we have this horizontal line sitting underneath SSE and M minus K. That represents addition. So it's saying, the F table is saying that you can add DF treatment to DF error to get DF total. And you can add SS treatment to SS error to get SS total. The mean squares, which are shown here, they're found by dividing each of the respective sum of squares by their degrees of freedom. And then the F statistic is found by taking MSTR and dividing by MSE. So the ANOVA table is just a structurally convenient and aesthetically pleasing way of summarizing step 3 of the hypothesis test that I'm going to show you momentarily. You don't have to use it, but typically we do use it. And questions that can come up on exams related to the F table, the very common questions are ones where you'll have partially completed F tables. So it's like, here's an SSTR, here's an F value, and here's a degree of freedom. Fill in the rest of the table. That's a very common kind of question. And using the relationships that we just talked about, it's very easy to kind of fill in all the gaps in the table from only 1 or 2 values. In fact, I'm pretty sure that if you know total sample size, you can always work out everything in the table from 2 numbers. Okay. All right. Okay, so here's the actual outline of the hypothesis test. Very standard approach, 6 steps. Step 1, null and alternative. There's no concept of being two-sided or whatever here. We're always testing the same things. Equality versus difference exists. Step 2, give the significance level, most often alpha 0.05. Step 3, compute the test statistic. Usually, again, on step 3, we insert an ANOVA table just to get us to the test stat. Step 4, critical value or p-value. They'll always give the same conclusion. You don't have to do both, but I'll illustrate both so that you have them. Step 5, decision. Step 6, interpretation. So very similar process to what we saw in the previous, in the review portion of the course, so lecture set 2 and lecture set 3. And throughout the course, you're going to see tons of hypothesis tests, and they all have the 6-step procedure. So in large part, what Stat 252 is really a course where you're introduced to a different hypothesis test on an almost a weekly basis. And the tests are always going to have the same structure, but what matters is determining when to use which test. That's the big takeaway from this course, or one of the big takeaways from this course, is assumption checking and using knowledge of the data characteristics. So using your understanding of the distribution of the data set to choose which type of test is going to be best depending on what the question you're trying to answer actually is. All right. So let's work through this example to finish the class today so that we have one ANOVA illustration under our belts going into lab assignment 2 and then the inevitable assignment 3 that'll be coming up on the weekend. Okay, so we're referring back to the minke whale data set, which is given on slide 9. Okay, so the summary statistics are given on slide 9. For that data set, let me just make a few quick notes here. Okay, so we had 39, 20, 28, and 14. So that should be 101, right? 2, 101, okay. All right. So the total sample size for this experiment was 101. So just to give a little bit of notational background here. So if we were to write little n is the sum from j equals 1 to k of nj, this would be little n is the sum from j equals 1 to 4. So the k represents the number of groups in the experiment. So we have 4 groups of nj. So that would be 39 plus 28. No, sorry, 39 plus 20 plus 28. No, iPad, don't do it. Okay, it's back. Okay, so for that particular, for the minke whale experiment, let's assume all of the assumptions are intact. Let's run the ANOVA to test for a difference among the 4 population mean lengths. Okay, so we're interested in determining if there's a difference in mean length of the minke whale at the 4 different depths. So we have h naught mu1 equals mu2 equals mu3 equals mu4. So you can see for the ANOVA, the null hypothesis in particular is very easy to set up. You just count the number of means and set them all equal to each other. The alternative is even easier because we can always use the same statement. Okay, so this always applies. In any situation, no matter how many means, you can just say h naught, not all means are equal, and you're done. We're going to test at the 1% significance level, so we're going to let alpha be 0.01. All right, so DF treatment is the number of groups minus 1. So we have k is equal to 4 because there's 4 groups in the experiment. So for DF treatment, we have k minus 1, which is 3. Okay, DF total is going to be n minus 1, which is 100. And then DFE is just going to be the difference between them. So n minus k, and that gives us 97. Okay, now let's compute the mean squares. So the mean squares are found by taking the sum of square and dividing by its corresponding degree of freedom. So in the first case, we have 37.0985 divided by 3. So this is going to be 12.36617. In the second case, for MS error, we have 87.2896 divided by 97, which is 0.8998. The F statistic is the MS treatment divided by the MS error. So that's going to be 12.36617 divided by 0.89989. So that's going to be 13.7418. Okay, so now we have our test statistic, 13.74182. So on step 4, we can take the critical value approach, or we can take the p-value approach. If we take the critical value approach, we start by sketching our F curve. Right. Our F critical value is going to be a value on 3 and 97 at 0.01. So we need an F table that has 3 degrees of freedom in the numerator, 97 degrees of freedom in the denominator. 97 is not a value that's going to exist naturally on the table, but we can still estimate what it's going to be using the tables. All right, so let's do 1, 3, 5, 7. Okay, so from the 7th page of the F table, we have our DF numerator, which is 3. Now, if we look at the DFD, you can see that we have jumps from 30, 60, 120. Our second degree of freedom is 97. The way that we would deal with this is to round down. So the rule is with degree of freedom, you always round down. So we're going to take 60, then we're going to go 0.01, and that gives us 4.13. Okay. So on the slide, we would write this is equal to F on 360. Actually, I shouldn't do that because it's not a true equality. Okay, so we're going to say use F on 360 0.01 equals 4.13. So we'll write this as, well, we'll just leave it there. So this value is now 4.13. Okay, our test statistic is 13.741. So we have F equals 13.74182. And we can see based off of the critical value approach, we're going to reject. Okay. Now, if we took the p-value approach, okay, so this is going to be F equals 13.74182. This part here is going to be the p-value. So the p-value is equal to the probability F is greater than 13.74182. Okay, so to solve this, we would go back to our F table. We're going to consider this whole block of numbers here. So for the same reason as we had just described, we're going to have to use 3 and 60 because these are the limitations of the table. And you can see in this case that our test statistic is larger than the largest listed value. So we have a value of 13.74182, which is greater than 4.73. So in this case, we would say that the probability that F is bigger than 13.74182 is less than 0.005. So we're going to have since probability F is greater than 13.74182, is less than 0.005, then the p-value is less than 0.005. All right. And then obviously based off of either approach, we reject H0. Okay, and then I'll finish the rest up on Monday. Okay, so that's an outline of how the F-test is going to work. We obviously have to make our concluding statement. On Monday, we'll just go over this, and then we'll look at another example. And then we'll move into lecture set 5, which is on multiple comparisons. Friday, we have the first lab quiz, or sorry, the first lecture quiz. I'll send out another email with details, but that'll be held through CrowdMark. You'll be invited to start the quiz at 12:55. You have until 2 o'clock. It's on lecture set 1, 2, 3. 3 questions total, with like a fourth question that's just you declaring that you agree with the policies. And yeah, that's it. So if you have any questions, please let me know. Otherwise, I might speak to you on Friday if you have questions about the quiz. Otherwise, I'll talk to you next Monday. Assignment 2 is still due Friday, and lecture lab assignment 2 should be available for you, which is due the following Friday. All right, so take care, everybody, and talk to you later. Yeah, so if the DF was 119, you would still round down. We want to be conservative, even though that sounds ridiculous. Yeah, no matter where the DF comes from, you always round down. T table, F table, any table.
I just have a question about the assignment.
Yep.
Just on number 10, when it asks for the confidence interval, are we doing a one-sided confidence interval like A is asking, or is it asking for a two-sided confidence interval?
Yeah, just do it. So the one-sided interval that you're referring to would be the one where you have the infinities in it.
Yes, yeah.
Yeah, don't do that.
Okay, so do the two-sided. Okay.
Yeah, just always do two-sided intervals for this class.
Okay, perfect. Thank you.
No worries. Answer, are you there? Yeah. Yeah, we said we would meet now, right? Yeah, go for it.